In this video, we will be looking at some examples of sinusoidal modeling, things that we did see in grade 11, but this time when we write our equation will be in radians. So let's start with example 1. The bird population in a certain wilderness area over time in years is sinusoidal. There are at least 6,500 birds. Well, that's already giving me some information there. And at most 10,000 birds. So that statement there has just given me my max and min value. So my maximum is 10,000 and my minimum is 6,500 birds. And I'll continue reading. It takes 2 years for the population to replenish itself once it starts to decrease. So that means from when it's at its maximum and it begins to decrease, 2 years later, it's back at its maximum, which means from maximum to maximum, that's your period. Sketch a graph to represent the number of birds over time for 5 years, start at the maximum, and then of course we will also find the equation of this function. Now, with just the information that they gave us, I can find quite a lot of other things. So if I have my max and min, I can also find my midline by averaging the values. So max plus min cut in half. And when I do that, I get 8,250. And now we can also find our amplitude by doing max minus min divided by 2, and when we calculate that, we get 1,750. So I'm going to get started with my sketch, and I do still need more values here, but just to get the sketch going. I have a minimum and a maximum. So here I'm going to have my population. I'll just say P for population. So let P represent population. And my maximum is 10,000. My minimum is a little bit more than 5,000, so 6,500. And then my midline is at 8,250. And I like to put just a little reference for me here for when I do draw my function. Okay, there we are. We know that the period is 2, so one cycle is going to take 2 years, and we need to do 5 years. So 1, 2, 3, 4, 5. Now, my period being 2 means 2 things. The k value for my actual equation is 2 pi divided by the period. So my k value is pi. And in terms of labels on my function, if my period is 2, every key point is going to be 2 divided by 4. So cutting that period into quarters, and that's going to be half a year. So every half a year, you will jump that special line. And it did say that we are starting at a maximum. So at 0 years, we're at 10,000. And because of that key point, I'm actually going to go in and label a little bit more. So 0.5, 1.5, 2.5, 3.5, 4.5. And now every half a year, I'm going to jump the line. So half a year, we're at the midline. 1 year, we're at the minimum. 1.5 midline. After 2 years, we're back at the start, and there's your first cycle. And now we're going to repeat for the rest of it. And at the 5th year, we don't get to complete our 3rd cycle. We've just done 2.5. And there we go. There's our equation. And on my x-axis, I do have time in years. So let T represent time in years. And now I'm ready to go with my equation. And just because of space, I am going to write my equation here, P at T, so population in terms of years. Now, I'm going to use this as my starting point to write my equation just to make my life easier. That is a maximum point, so I'm going to use the cos function, and the amplitude is 1,750 cos. The k value is pi times time, and there is no phase shift because my starting point is at year 0, and then plus my midline. And there we are. If I wanted to force a sine function, I would change my starting point. I can use this here, and that would be a reflected sine, or I could work backwards, and at year negative 0.5, that would be a positive sine function. Either one would be fine. So let's say I wanted to avoid a reflection. There's my amplitude, there's sine, there's the k value, but now I'm going to shift to the left, 0.5, half a year, and there we are. So that's another version. Or I could have had a reflected sine, and instead of going left, I could have gone right, 0.5. It all depends on your starting point. But there we are. Our first example, it was a population example. We were given the max, the min, the period, and with that, we were able to get the rest of our properties. So let's try another one. On a merry-go-round, each horse moves up and down 5 times in one complete revolution of the ride, which takes 15 seconds. Each horse rises and falls a span or a range of 50 centimeters, and the horse is 100 centimeters high at its resting or center position. Sketch the graph to represent the height of the horse over time for one complete revolution of the ride, starting with the horse at its resting position and heading up. Okay, there's quite a bit of information here that we have to decipher. Well, first of all, our resting position or our center is at 100 centimeters, so that's going to be my midline. Now, when it says this range of 50, that means if the horse is at a midline of 100, like this, it goes up, it comes back to the midline, it goes down, it comes back. This is the motion that the horse is doing. And this motion spans 50 centimeters in total. And if we split that in half, that means 25 centimeters above the midline, 25 centimeters below, which would make my maximum 125, my minimum 75, and my amplitude 25, because 25 above the midline, 25 below the midline. Next, I have information about the period. The horse moves up and down 5 times in 15 seconds. So the period is going to be, in 15 seconds, we have 5 up and downs. That means 3 seconds per cycle for the horse, okay? Which means our k value would be 2 pi divided by the period. And in terms of my scale, when I draw my graph, the key point is going to occur 3 divided by 4 every 0.75 seconds. And we are told that we're starting at the resting position and heading up. So let's draw a sketch so that we can create our equation. So T for time, H for height. I'll write my let statements in a second. The midline is at 100, so I'll put that there. The maximum is 125, and the minimum is at 75. And there we go. We're starting at the midline, so at 100. And again, I'll just put my reference lines here. Okay. And I need to go to 15 seconds because it says for one ride. So I need to make sure I include that. And each cycle, each period is 3. So I'll say 3, 6, 9, 12, 15. And because we know each period is 3, each of these has to get cut into 4 sections because it's going to be every 0.75 seconds that we jump. And that would do it. I'm not going to label each of the tick marks, but it is every 0.75. So 0.75 seconds later, I'll go up to my max, and then to my midline, to the minimum, and then after 3 seconds, I've done 1 up and down for the horse. And now I continue. At 6, we've done the second. At 9, we've done the third. At 12, the fourth and last one. At 15, we've completed the 5th up and down of the horse. And here's our function. Let's write our let statements. Let h represent the height in centimeters. Let t represent the time in seconds. And now my equation, h at t, because we're starting at the midline heading up, the most efficient function would be sine, a positive sign. The amplitude is 25. The k value is 2 pi over 3 with no phase shift. And the midline is 100. And there's your function. Part B says, when does the horse reach a height of 112 centimeters during the first 2 cycles? Visually, 112, let's say, is here. And we only care about the first 2 cycles. So I'm trying to find these 4 points. So let's set our equation equal to 112, and we're going to be solving. And while I do that, I am going to simplify my angle to just theta. So temporarily, I'll set theta equal to 2 pi over 3t. And now I'll bring the 100 over. That gives me 12. I'll divide both sides by 25. And here's the ratio I will be solving. I'm going to take a sine inverse to find alpha. And I also see that my ratio is positive, which means sine is positive in quadrants 1 and 4. Now when I take sine inverse of 12 over 25, I get approximately 0.5. So in quadrant 1, theta is 0.5. In quadrant 4, theta is 2 pi minus 0.5, and that's approximately 2.64. So these are the values of theta in one cycle, but we're not trying to solve for theta, we're trying to solve for time. So we have to bring back this. Let's replace our thetas with 2 pi over 3t equals 0.5. And now when I try to solve for t, I'm just going to multiply both sides by the reciprocal, because that will mean the 2 pi's cancel out and the 3's cancel out, which is perfect. And whatever I do to one side, I do to the other. So the first time I get is approximately 0.24. And I'll do the exact same thing for the quadrant 4 value. So I'll multiply both sides by 3 over 2 pi. And when I do that, I get 1.26. And if I look at my sketch, that seems decent. It seems reasonable with my scale. But of course, I also want the second cycle. So I have to add the period. And the period is 3. So I'll add 3 to get another set of solutions at 3.24 and 4.26. And those are all of my values. And I'm just going to write my therefore statement where I have space, which is right here. Therefore, the horse is at a height of 112 centimeters at 0.24, 1.26, 3.24, and 4.26 seconds. And there we are. Very similar to grade 11 in terms of finding the equation, just we're using 2 pi over the period for the k instead of 360 over the period. And then in terms of the solving, also very similar. It's just our angle is a little more complicated, so we can replace it with theta like we've been doing, and then you can solve for t later on once you're ready and have established good theta values. Let's go to our last example. All right, we have a Ferris wheel example. A Ferris wheel has a radius of 7 meters. The center of the wheel is 8 meters above the ground. I'm just going to go to my little sketch here. The radius is 7 meters. The center here is 8 meters above the ground, which already tells me the center is the midline. 7 above that is 15 for the maximum, and 7 below that is 1. So I've just established my max, my midline, and my minimum from that one little sentence. Oh, and actually, my amplitude is the radius. The Ferris wheel rotates at 15 degrees per second. So 1 second, 15 degrees are rotated. But we know a full rotation is 360. So for our period, we can take the 360 degrees we need for one rotation and divide it by 15 degrees. And when we do that, we get 24. So that means your period is 24 seconds. So for my k value, that would be 2 pi over 24, which is pi over 12. For my actual sketch, every key point will occur, divide that period into 4 pieces, every 6 seconds. So let's go ahead and draw a sketch. And it says, sketch the graph to represent a person's height over time for 1 complete revolution. Okay, so that means I can stretch this out. 1 rotation is 24 seconds. And every 6 seconds, I have a key point. So here we are, time is there, height is here. I'll label my minimum, my midline, and my max. And the person gets onto the ride at the lowest point, and every 6 seconds we switch lines. And there we are. There's the first revolution, and that can keep going. Okay, so let's write our let statements. Let age represent height. Let t represent time. Height is in meters, time is in seconds. Because our starting point here is at a minimum, I think the most efficient would be a reflected cos, although you could do a sine with a phase shift. So my amplitude is 7, so -7 cos pi over 12 for k times t, no phase shift, plus my midline of 8. And there we are. B says determine the height at 29 seconds. Well, that's just me replacing t with 29 and going to my calculator. And make sure your calculator is in radians. So -7 times cos, and for your angle, you'll have pi over 12 times 29, close that bracket, plus 8. And if you punch it in correctly, and you're in the correct mode, you should get 6.19 meters. Okay, so therefore, at 29 seconds, the height is 6.19 meters. And the last question says, when does the rider reach a height of 11.5 meters during the first minute? So So we're looking from 0 to 60 seconds, which is going to be a bit more than 2 rotations. So I'm going to have to set my equation equal to 11.5 and then solve. All right. So 11.5 equals -7 cos, and I'm just going to simplify that angle. So theta equals pi over 12t, and now I'm going to solve. So bring that 8 over. When I bring it over, I'm left with 3.5 equals -7 cos theta. Divide by -7, and that actually brings in a ratio that should remind us of a special triangle, that -1/2. Cos is negative in quadrants 2 and 3, and to get an adjacent of 1 and a hypotenuse of 2, just thinking of your special triangles, it's going to be pi over 3. If you want the diagram, here it is, adjacent over hypotenuse. So there's the verification. So in quadrant 2, theta is going to be pi minus pi over 3, which is 2 pi over 3. And in quadrant 3, we have pi plus pi over 3, which is 4 pi over 3. And of course, we're not trying to solve for theta, we're trying to solve for time. So I'm going to go in and replace my thetas with pi over 12 t and just like before, I have that pi over 12 in front of t. Multiplying by the reciprocal will wipe it out on the left. So I'm going to do the same thing on the right, so that I'm left with, the pi's cancel out here. 12 over 4 can simplify to 4. So I just have 8 seconds. Now, if you didn't want to simplify the way I did, you're more than welcome to actually do the multiplication. So it'd be 24 pi over 3 pi. And here you'll see, oh, the pi's canceled out. 24 over 3 is 8. That's perfectly fine as well. And then I'll do the same thing on the other side. I'll multiply by 12 over pi. And the pi's will cancel out again. And if I clean this up, I will get 16 seconds. So those are the first times in the first cycle. But I was asked for a full minute, which is 60 seconds. So let's add our period a few times. Our period was 24 seconds. So let's see how many times we can add it on. When I add 24 to 8, I'm at 32. When I add 24 to 16, I'm at 40. Let's try adding another 24. If I try to add 24 to 32, that's 56. That's good. If I try to add it to 40, that takes me to 64 seconds, which is outside of the bounds that I asked for. So now I can go in and write my therefore statement. Therefore, the rider is at a height of 11.5 meters at 8, 16, 32, 40, and 56 seconds. And that's it for your sinusoidal modeling. You have your sketching, you have your finding equation, you have trig solving, lots of great skills here.